This is our special webinar on how to make the best decisions under conditions of risk and uncertainty using Analytic Solver. And this webinar is an outreach from our dedicated customer success and support teams to make sure you're getting the most out of our products. My name is Dr. Sima Maliki. I am pleased to host this webinar and welcome you. During this webinar, we walk through the key concepts and solution methods for making the best decisions under conditions of risk and uncertainty using Analytic Solver. And we are going to start with a quick overview of stochastic optimization model components. Then we practice solving models with chance constraints, recourse decision variables, and we also review a simulation optimization application. So we are going to learn about modeling uncertainty, and the good news is Analytic Solver has a wide range of capabilities for analyzing and solving decision models that must allocate your scarce resources in the presence of risk and uncertainty. You have access to state-of-the-art technology and stochastic programming and robust optimization methods, fast performance. In fact, Analytic Solver has the fastest performance in simulation optimization, many times faster than its competitors. Also, it delivers unique capability to define and solve problems with wait and see or recourse decision variables. So in conventional optimization, all the parameters are assumed to be known numbers with certainty. But in almost all business and engineering problems, there is at least some uncertainty in the values of parameters. And what do we mean by uncertain parameter? In terms of optimization, a parameter of your optimization model, this can be your objective coefficient, your constrained right-hand side that is subject to uncertainty. So an optimization problem that includes uncertainty is usually called a stochastic optimization or a stochastic programming problem in general. Now let's talk about some more concepts, some key concepts, and a little introduction for those of you who are new to these concepts and the way that we look at these problems from perspective of Analytic Solver. So the key concept is that a certain parameter has a single known value, just like this shape, certain parameter. An uncertain parameter has many possible values, and we call each such value a realization of the uncertainty. So these are three uncertain parameters, and each such value is a realization of the uncertainty, right? So this uncertain parameter can take anything from, like, say, 3.5 to 7.5. It's a triangular distribution, right? This one looks like a normal, and this one is like a uniform. Okay. We divide uncertainty into two general situations. In some real-world problems, we are uncertain about the value of a parameter today, and we will remain uncertain about its value in the future, and we have to make decisions in the presence of uncertainty. Say in an engineering design model, there is uncertainty about exact resistance of an electronic component, and this uncertainty may be reducible or irreducible or maybe something inherent in nature. But if you have, for example, better data collection, measurement, or calibration, it may be reducible. However, these steps may be impractical for us, okay? So we have to deal with uncertainty and make our decisions in the presence of uncertainty. In other real-world problems, we are uncertain about a value of a parameter today, but we will know its value with certainty at some point in the future. For example, marketing or finance model. We have a competitor price or next year commodity prices or interest rate that are uncertain today, but they will become known at some future date. We say that uncertainty will be resolved at a future date, and at that date, its many possible values, remember it's uncertainty, right, will be reduced to a single value. and the uncertain parameter will become certain. If we are dealing with uncertainty that will not be resolved, we must find values of decision variables that yield feasible or nearly feasible solution of many possible realization of the uncertainty, okay? On the other hand, if we are dealing with uncertainty that will be resolved at a future date, you can ask what are the decisions you must make here and now before the uncertainty becomes known, and what are the decisions you can make on a wait and see basis after the uncertainty is known. We call the decision variables that we must make here and now normal or first stage variable. Okay, so basically in Analytic Solver, if you want to define a normal decision variable, you select a cell, go to decisions and call it normal. Cell A1, right? A normal decision variable. Solver will replace this number with an optimal value when problem is solved. Now, we call the decisions you can make on a wait and see basis after the uncertainty is known recourse or second stage variables. Okay, so to define a recourse or second stage variable, just go to select, for example, cell A2, decisions, recourse. And under optimization, now you can see we have a recourse decision variable. At the time the optimization is performed, a single recourse variable effectively represents an array of solution values, one for each realization of the uncertainties in the model, okay? But later it will change, and we'll talk more about recourse models later, okay? This is a general classification of stochastic optimization problems based on how we look at them in our user guides and how we have categorized the solution methods. So you can see the solution method available in Analytic Solver for each gallery written on the right side of the slash. But in general, there are three solution methods currently supported by Analytic Solver: robust optimization, stochastic programming, and simulation optimization that can be applied to these problems according to their structure. So if conditions apply, Analytic Solver can transform your model, a model which objective or constraint depend on uncertainty, into a deterministic equivalent or robust counterpart that may be larger, but objective or constraint of that new model, the transform model, no longer depend on uncertainty. And we are going to solve the transform model for you using a traditional solver engine and translate the results into a solution for the original model. For successful transformation, usually the model must have uncertainties that are independent of decisions and have objective and constraints that are linear or certain other functions that I've described here of decision variables. Okay, but you have to ensure that all top-level formula cells containing the objective and constraint represent only single values. So you can use statistical summaries of or arrays of sample values. For example, when it comes to objective, the most common practice is to use maximize or minimize the expected value. So when you go to objective, now you can see you have minimization, you have normal objective, but you also have expected and chance objective. If your constraint depends on uncertain variables and normal decision variables, we must specify what it means for the constraint to be satisfied. There are many possible realizations for the uncertain variables, but only single values for the decision variable. Analytic Solver must find values for the decision variables that cause the constraint to be satisfied for all, or perhaps most but not all, realizations of uncertainty. For example, we can specify that the constraint must be satisfied 95 or 99% of the time. Therefore, it can be violated 5% or 1% of the time. We call this a chance constraint. This is one form of chance constraint that the criteria must be satisfied for all realization of uncertainties up to a given percentile, say 95 percentile, and it makes it a var or value at risk constraint. This is the VAR or var constraint, okay? So if you have a var constraint with probability 95%, it requires that the constraint be satisfied, not violated, 95% of time, and it says nothing about the magnitude of violation that may occur on the other 5% of the time. So if we get a bad outcome hitting the tail, how bad it will be. And sometimes this is concerning. You have a very bad loss. And in old days, bank would just be concerned about the chance that they would hit the left tail, and they wanted to make sure it is less than a certain amount, but then they figured out that wasn't good enough. So if you want to restrict, what do we do? So there is another type of constraint we call CVAR, conditional value at risk. CVAR 95% A less than B specifies that expected value of all the realization of A1 up to the 95% and up 95 percentile must be less than or equal to B1. CVAR basically restricts how bad that event can happen. And here we have a visualization for that. If a constraint depends on uncertain variables and recourse decision variables, then the solver must find an array of values for each of the recourse variables responding to realizations of the uncertain variables. For examples today, we are going to use the shipping examples. You have access to all of them, so don't worry about writing anything or saving these models. But I'm happy also to send you all the information. So go to help, example models, and you can see in Analytic Solver, we have stochastic optimization examples and simulation optimization examples. So let's click on stochastic optimization examples. And for today's webinar, we are going to look at gas company chance, and then we are going to compare it with gas company recourse. With gas company chance, you will see how a problem with uncertainty can be formulated with a chance constraint and solved using robust optimization. With the gas company recourse, you will see then what is a wait and see approach and how to define recourse decisions to obtain a better optimal solution. So let's just quickly go over the model so you're all familiar. If you want, you can open it at the same time. We have a gas company that purchases natural gas from suppliers and resells it to consumers in the service area. And consumer demand for year 1 is 100 units, but it is uncertain for year 2. The company must meet demand with high probability, or it will encounter some public relations and regulatory problems. The price of gas known to be $5 per unit, but for second year, this is uncertain and depends on some beta distribution. This is the uncertainty in the model. Let me just double click. This is a beta distribution. This is called an uncertain variable dialog in Analytic Solver. And you can see we have PDF, CDF, reverse CDF, and then in the right side, you have different drop downs. You can adjust the parameter, and you have control parameters and much more. Also in this drop down, you have analytic moments, percentile, chart type, and so forth. So let's close that. The gas price depends on this beta distribution, and similarly, the demand for year 2. And there is some more information on the top saying that if the weather is very cold, demand may reach 180 units, price may reach 7.5, but if the weather is warm, demand may remain at 100 and the price may remain at $5 per unit. What is the goal of the company? To minimize its total cost of purchased and stored gas. So what are our decisions? Let's look here, look at the decision variables. And we don't have a recourse decision variables, right? We have to deal with uncertainties here and now. How much gas to purchase and resell to consumers this year? Year 1. How much gas to purchase this year and store at cost of $1 per unit for the next year use? And then how much to purchase and resell to consumers next? And all of our decisions are normal and here and now decisions. The constraint is that the company must have enough gas to meet next year's uncertain demand with high probability. So when I say high probability, it might be very obvious to you that we have to use a chance constraint. So Let's erase all the drawings and let's look at the chance constraint. You can see under Analytic Solver, and let's double click, and you can see that we have D38 must be greater than 0. So we have to meet the demand in year 2 with high probability, and this means for us 95% of the time. On the constraint drop down in this section, you can actually choose from normal. You have probably used normal a lot, but you can use var, cvar, and there is also another type called uset. And you can find more information in the user guide if you want to learn about uset type of constraints. And then we have the chance constraint. Let's look at objective. So remember, we have to have summary statistics for objective. Here we are using minimum. And if you see, there are different types for objective. And here we are choosing expected or the average. So you have normal objective, expected, var, cvar, or uset. You could also use define your summary statistic, go to Analytic Solver, go to results on the simulation model group. Let me highlight it for you. So how to define summary statistics. If you're not familiar, just go to results, statistic. For example, you can calculate the mean or a standard deviation. So just a summary statistic. So if you calculate the mean, then you can use that mean cell as the objective, normal objective, because it's a summary statistic. Okay, now let me show you a few things. We want to learn about the structure of this optimization model. And Analytic Solver here is going to use robust optimization and automatically transform this stochastic linear programming problem and all this expected value of objective and chance constraint into a larger conventional optimization model, then solve it for us. The robust counterpart, it is called robust counterpart. It will solve it and gives us the result, which is a single LP. So to see the difference, I'm going to show you something. So I don't know if you have used analyze option. There are a few ways to do this. So there's this button here. If you choose the drop down, there are two options: analyze original model and analyze transform model. And this is a very good time to use both of these. So if I analyze the original model here, it will actually look at this stochastic optimization problem without doing any transformation, and then it gives us some information. So we have all the variables. There is only one uncertain variable, and the two of the functions are dependent on this uncertain variable, and we do not have any recourse decision variables. And you can see we have chance constraints, right? Another way to get this information is go to reports, go to optimization, and you can get an uncertainty report. Where are the sources of uncertainty? Where are the formulas, and also the statistics of the model? So we have one uncertain variable and two uncertain functions. So this is before any transformation. Now we can also analyze the transform model. So let's click on that. I turn on the guided mode so you can see step-by-step what information it can give you. So this is automatically telling us that after analyzing the model, it was able to automatically transform this model with uncertainty into its robust programming equivalent, deterministic equivalent. The next step. Now you can also look here that model type is now LP convex. We do not have any uncertain variables or functions or dependencies, and there are zero chance constraints. Let's go ahead and click on optimize to solve this optimization problem. So the first one, the original model was stochastic LP, and then the transform model was just an LP convex. And I'm going to show you there is an option for transformation of these models, because we have advanced users here. So the chance constraint, we are using dnorm, and there is an option called auto adjust chance constraint. This is set to true, and I will explain to you what this means. Okay, with all of this, let's just click on optimize. So again, guided mode, continue, and here are the results. If you look at the answer report, you might wonder why it has been solved multiple times, right? I will explain that to you in a few minutes. We got the answer. Here are our decision variable values. For first year, answer is 100. Second, how much to store is 0, and then gas to power resale is 159.06. The best thing to do if you want to get the optimization, the objective results of the transform model is to go to report, and you also get more information. Go to optimization and get an answer report after solving this stochastic optimization problem. Get an answer report, and let's look at this answer report together. So here is the final value of the objective, decision values, and also we have some information about the constraint. So we requested 95%, and for the chance constraint, it gives us 95.7%. But remember, the autocorrect chance constraint was on. So if that's off, you may get a different result, basically more conservative solution. Now let's go back to the model and let's go to platform tab. I'm going to turn off the auto adjust chance constraint to false. Now let's go ahead and optimize again. Continue. Next step. And here are the results. First of all, you will see immediately that it's not repeated anymore like that, like previous time. And you will also see this new button, it shows up here on the task pane. Now that we solved the model, let's get a report, answer report, and let's look at the results for the chance constraint. And you can see that the chance constraint is actually satisfied 99.5% of the time. Okay, so this is a very conservative solution compared to what we expected, which is 95%. That auto adjust chance constraint allows us to rerun the model multiple times and actually adjust that to match the requested value from the user, which was 0.95, right? Something close to that. So, and if you go back here and rerun with resolve the model and auto adjust, then it will does the same thing for you. You can see it repeats everything, right? And then if you get an answer report again, it should be back to the 95.7. Okay, gives you a more closer match to what you actually requested. If you set auto adjust to true, will automatically improve the solution for you to match what you requested. To get the expected total cost here, basically if you double click here, you will run 1000 trials and get the expected total cost, help, example models, and then stochastic optimization example, gas company, recourse. So the recourse is with the assumption that at least some or all the uncertainty will be resolved over the horizon of interest. And the problem is called two-stage. First, the normal decisions are going to be made at the first stage before the uncertainties are known and resolved. And recourse decisions are made at the second stage after the uncertainty is resolved. In the first part, you will see that solver will find single value for normal variables, but multiple values for recourse variables because uncertainty is not known. So if we get multiple values for each realization of uncertainty, that satisfies the constraints and optimizes the objective, okay? But then I will show you how can we see the change uncertainty to a certain situation and then solve for recourse variable. We can do this if the business situation permits us to make decisions of next year on a wait and see basis, right? So it doesn't apply everywhere. Here we assume in this business situation, we can make the decision of how much gas to purchase next year on a wait and see basis after the uncertainty of whether is resolved, a so-called recourse decision discussed in the beginning, right? So the gas supplier might accept our purchases or purchase order next year and not require us to commit a specific amount of gas this year for delivery next year, right? So that's the assumption, and some scenarios you can do this. If the business situation permits you to make some decisions on a wait and see basis, it is crucial that you actually include this in your optimization model. And if you don't, you may find an optimal solution to the wrong model for the actual business problem, which might have seen that we might have seen a lot happen for people for two reasons. Number one, they are not familiar with the concept, and number two, the software people are using, if they are not Analytic Solver users, doesn't allow them to create models with recourse decision. But this tool is available to you, and a lot of people use simulation optimization. Unfortunately, it is popular, but it has no concept of recourse, and Analytic Solver is quite unique in offering this capability. So let's learn to actually use this tool fully. So let's look at the task pane. The model is already predefined, and you can see now we have a recourse decision for E33. So E33, right? How much gas to buy and resell year 2. Here you also see that the objective is the same. We are minimizing D40, expect value of D40. Okay, and the only thing different is actually the amount of gas to purchase next year appears as a recourse decision variable, and we don't have a chance constraint anymore because it's a normal constraint. And it's actually, we change it to a greater than or equal form because we expect to satisfy next year consumer demand exactly. Again, if you just go ahead and analyze without transformation, analyze original model, it's a stochastic LP model. And if you change it, it's going to be a linear model for you, right? But let's go ahead and click on optimize to solve this problem. So let's go ahead and click on optimize to solve this problem. Welcome to guided mode, continue. Okay, Analytic Solver again able to transform this model and get the optimal solution for us. Okay. So now we have the values, the optimal values for our first stage decision variables. So which is buy and resell for year 100, do not store anything. And then you see I have something in the second stage 2 variable for the recourse variable. But in fact, I want to show you that this is not one value. This is an array of 1,000 different values. So I'm in tools, and here you have 1,000 trial levels, the default value, and you can choose which trial to display. So you can actually cycle through individual trials and follow on the workbook. So you can see that the stage 2 variables are changing as I am showing you each different trial. For the course variable, we discussed that we're going to have an array of possible values, but then later, when actually the uncertainty is realized, then we can solve for recourse variables. We have many possible values at optimal solution for our recourse decision variable, one for each realization of uncertain demand. So you can cycle through, or you can actually look at a histogram. So let's double click and you can see a histogram of all 1,000 trials values for this recourse variable. This is the part that's very important. It's not discussed in the user guide, but I want you to be familiar because that's actually what should happen in reality, right? Assume time has passed, say 6 months or 1 year, and the uncertainty has become known. Basically, this beta distribution is no longer an uncertain variable. So, and similarly, the gas price and demand are exactly known. How do we do that? Just to show you one quick trick. If you want to change the realization of uncertainty and make it certain, there is a little quick option here. Basically, I want to replace the beta distribution with a fixed value, hence to fix the demand on the gas price, right? So there's a control parameter called lock on the control parameters, right? And let's just replace it, say, with 4. Okay, just as an, oh, sorry, in the wrong place. Lock 4. So let's click on save. Once you lock it, all of these will become certain values, okay? Actually run one simulation and you see we now get only one value. Now we can solve the model for the recourse decision variables. How do we do this? So this is after the uncertainty has become known. Under optimize, there is a drop down for solving optimization. Solve for recourse variable. This is what we're interested in. So let's click on solve for recourse variable after the uncertainty has become known. So we solve that and actually get an optimal value for the recourse decision variable to meet the demand according to realization of uncertainty. And that's how you solve the second stage. Any questions? I'm going to move on to last example. Let's erase all the drawing and go to help. Example models. Now let's choose one example from simulation optimization group. Quickly look at that and compare what you can do. This is a project select, very famous, typical application for simulation optimization. We have 8 different capital projects that are proposed for funding. Each one has a known initial investment. Each project has a 90% chance of success. And if a project succeeds, it will have an uncertain but positive future cash flow. And cash flow, we are modeling via a triangular distribution for each of the projects. The funding of all 8 projects would require a total initial investment of 2.5 million, but our capital budget is only 1.5 million. We must choose a subset of projects to fund, and the goal is to maximize our expected total future cash flow, okay, in this cell, which is a mean of total cash flow in this cell, which is calculating the total cash flow for you. These are all binary decision variables. Okay? And just to get an idea, let's go ahead and just analyze original model. And we have a stochastic LP, MIP, because we have integer variables, right? So it's a mixed integer model. So we are asking Analytic Solver to find the best combination of projects by finding 0 and 1 values for selection of variables in this column I 18 to 25, and to maximize G32, which is our expected total cash flow. Okay, we are going to solve this problem using simulation optimization. So let's go ahead to click on Analytic Solver. If I can just click on Optimize, and then we are using evolutionary engine. It's a simulation optimization. We are not making any assumption about the structure of this model. So we're using evolutionary engine. You're familiar for solving non-smooth problem to actually solve this simulation optimization. And I choose these settings to be comparable to other software which you may have encountered. Simulation optimization is a very general approach that can handle nonlinear and non-smooth functions. It assumes no structure in the model, and in general, the number of steps can grow exponentially with the number of variables and constraints, which is quite obvious. So now let's look at the outcome. So we solved the problem with evolutionary engine. This is great result, and here are the cash flow, the expected total cash flow. Well, we did some work, took few seconds to solve this model, but we can do much better actually when it comes to these models. We actually can allow Analytic Solver to at least try to do the automatic transformation. But I want to show you that there's another option here that I set to force Analytic Solver to use simulation optimization, and this is solve uncertain models. Okay, solve uncertain model, again on the platform optimization, and you can see that we have multiple options. You can force Analytic Solver to choose your desired, for example, stochastic transformation, stochastic decomposition, or just set it to automatic. At the same time, I force the engine to be evolutionary engine. I can actually go ahead and choose automatically select engine. So that Analytic Solver, when it analyzes structure and chooses the best method, it can choose the best engine to solve this problem for us, okay? And now let's go ahead and we can put the variables back to 0, just using this button, and then we can click on Optimize, Continue, and here it is. Actually, this model is also transformable within Analytic Solver capabilities, and click on Next Step. Just in a matter of seconds, and the automatic engine selection, we use Groby engine. You can use LPMIP or other engines to solve the problem, okay? And you see the difference, how quickly it was solved if you are using a better approach, and here we use deterministic equivalent. This was a small problem. Now imagine you have a very large simulation optimization. If you're able to use the capabilities of Analytic Solver and use these other methodologies, then it will save you a lot of time and actually gives you a better answer. We have a proven global optimal solution. So basically, there was no need to run hundreds of Monte Carlo simulations. Today, we explored a few of Solver capabilities that are available to you. We learned that Analytic Solver has the full spectrum of capabilities for analyzing and solving decision models that must allocate scarce resources in the presence of risk and uncertainty. We look at few examples, and learned that we can work with stochastic programming, robust optimization, and we have the fastest performance in simulation optimization, many times faster than competitor products. And we learned that we can use the unique approach of solving problem with wait and see or recourse decisions. Without the right tool, your resource allocation problems under risk and uncertainty can become difficult and expensive to solve. But now that you're aware that the capability of solving large-scale optimization problems with uncertainty in Excel or beyond it is already yours. And there's much more to Analytic Solver. All of these capabilities are available within Raison, which is our deployment platform, and you can do much more with our products. Thank you so much, everyone. We hope this webinar refreshed your modeling perspective and equipped you with some new tools. Have a wonderful rest of the day. Bye for now.